Okay, no issue. That's great. So let's focus on machine learning issue. Um, Sometimes you want to understand more things about some learning algorithm or the trained models, for example. And sometimes if the model is very good, but sometimes your model can be very bad when solving some problems. And sometimes you want to understand what is the main reasons why the model can be very bad or inconsistently, for example. Okay, so in those cases, um, sometimes you need to explore in more detail about the models, about the data or the algorithm, the training algorithm, for example, right? Okay, so in this lecture, we will study about some aspects that can help us to analyze the error of a model. Let's focus on very simple situation, simple setting. It is a supervised learning problems, right? And in this case, we assume that there exists an unknown function we denote by y star that can map from 1x to y, right? And this function can be complex sometimes, and often complex in practice. We do not know, right? But in practice, we can collect some example about x and y. For example, this is one pair, this is another pair, or another pair like this, right? And our task is to find the unknown function based on this data set. That is a general learning problem. And here, sometimes x, it is the input, and y, it is the output. And it can belong to an output space, right? X can belong to the input space. And this function, sometimes we call that the labeling function or a true function, right? The truth. For example, uh, the function, the unknown function can be here, can be very complex like this, right? And in practice, you can collect some x and y around this area and around this area, right? So based on the data set, you know some information for the unknown function. Okay, and in practice, many things are hidden, except the training set, right? For example, the way we collect the data sometimes can be missing. Or in other words, we sometimes we say that the data distribution, the way we collect the data, the process that generates data sample, right? And it is unknown. And of course, in this way, so sometimes we call that is a data generation models. This is just one example. Um, the green line here, a blue line, represent the density of the data distribution. Okay, and in this case, our distribution can be complex. And in practice, you can collect some sample around this area and some around this area, and few sample can be around this area, right? Okay, and the unknown labeling function can be here, right? So it means that many things here can be unknown. The labeling function and the sampling distribution, right? The way our data sample can be generated. And of course, in practice, in order to enable us to analyze something about the problem, about the models, we often assume that the data here are generated independently, right? from the same distribution. Or in other words, IID assumption should follow, for example. Those samples should be independent, right? And in that case, we can use that assumption to analyze something easier. But of course, in practice, this assumption sometimes can be violated, right? Okay, so for the learning problems, we have two unknowns. One is data distribution, and the other is a labeling function, right? So, in general, this is an intractable problem. And one way we often use this is to use a simpler function, right? To approximate the unknown function, right? And the simpler function here, we can work in practice. We can easily work with in practice, right? And this function, sometimes we call that a predictive, a model, right? Okay. And in order to find that specific models, we need one algorithm, right? That receive one data set, one training set, and then produce one specific model, right? So in that case, we call that the learning algorithm. And sometimes we say that the learner, and in fact, we can consider a learner to be a mapping, right? It can map from one training set to one specific model. Okay. Okay. And up to now, you already know many different algorithms, right? And of course, those algorithms often does not know about the true labeling function or the true data distribution, right? Okay. One question is where our model come from? One way in practice we often do is we can use one type of function, right? Or a family of functions. Or sometimes we call that one architecture. For example, we use a linear model. It means that we are working with. We choose a family of linear models, right? And we will find one specific one to approximate the unknown function, right? That's the way we often use. Okay, so, and this set we sometimes call the hypothesis space, right? Or the model space. This is just one example. A family of linear models, right? And of course, in practice, in order to analyze error, sometimes we can compute the error from a data set, right? If we compute it from a training set, sometimes we call that the training error, right? But that is not the goal. The main goal when we work with a learning model is we need to minimize the expected error, the population error, right? That is the error average over all member in the data space, not just a simple training set, right? If that error is small, then you have a good model, right? And in in theory, we can define that population error to be like this. We denote by FP8 to be the expectation of the loss of the individual prediction, right? Here we denote F to be a specific loss. For example, we can use a square loss, absolute loss, or zero-one loss, right? And when we compute the loss in a specific data set. Sometimes we call that empirical loss. Okay. And of course, when we train the models, we are trying to find one specific members in a family age, right? That minimize the population error, the test error. Sometimes we call this the test error. Okay? That is the ultimate goal of the training process. But sometimes, and often in practice, we cannot achieve this goal. It is not easy, right? Because in practice, we only have a finite number of samples. And here, the definition of this is a population error, the average error over the whole space. Okay. So that's why it is very, very hard to, to compute, to work with. It will just minimize the training error. Sometimes it can be known as fitting. We fit a model based on for a given data set, for example. But that is not our goal, right? It is not another goal of learning. Okay, so just one example. We have the two function to be green light here, but we use a very complex function, red, and it can approximate the whole training set, right? But here you can see that this function cannot approximate this one, right? It should have a very large error on average. Okay, and if a training algorithm just focus on the training loss, it is sometimes known as empirical risk minimization, okay, or EIM. It is one of the most classical algorithms to train models. We just focus on training error, and we train a model that minimizes error, right? That's all. And of course, in practice, this way can lead to some overfitting model, right? But in the case, if we have a very large number of training samples, these methods can be very good according to the law of large numbers, right? Because by that law, we know that this empirical error will go to the expected error, right? But it's in the case of very huge data set. So this method is good. But in practice, sometimes, and in many cases, our data set is very small or just average, for example, right? So this approach may not match, and we may easily get some overfitting model. So that's why in practice, we often use one way, it is regularization, right? And the idea is very simple. We can add a term, a regularization term here to penalize complex model, right? When we do training. And G8, we often call, we often use some way to measure the complexity of the model. And lambda here, it is constant, non-negative constant, right? And this term is trying to penalize some complex model. And by this way, we are trying to feed on the training data, but we just find some simple model, right? So we are trying to balance the complexity of the model and the fitting on the training set. And by this way, we can hope that the model can trade for test error, right? We can hope that the test error can be small. That is a regularization. Okay. So next, let's analyze the error. After training, we can obtain a model we denote by S0. And of course, we want to understand its ability for future prediction, right? Or in other words, we are considering its generalization ability, right? How well it can work with unseen data on average. And of course, in practice, our trained models can be here, but when we are trying to minimize the training loss, the minimizers can be different. Even we just focus on the training error. But the ultimate goal of the learning problem is we need to find the minimizers of this problem, right? The best function, the best model in the family we already choose. Okay, but in practice, the trained models can be very different from those ones, right? And of course, it can have some error. So let's analyze the error. We can express the error of the trained models. We consider the difference between the error of the trained models and the error of the ideal model. And in fact, it is zero, right? This this error should be zero. Hey. So from this one, we just add one more term and plus that term. It is similar, right? But now we arrive at two terms. The first two terms here represent one quantities. Sometimes we call the estimation error. And that error is the difference in quality of the trained model and the best model, right? We try to see that. If this error is large, you can show that the trained model can be very bad. And of course, we are trying to minimize this, right, when we train a model. And of course, these quantities represent how good a training model is. For one problem, we may have different learning algorithms, right? And in practice, you need to choose a specific one for your problems. And if your learning problem is very strong, then with a high probability, it can return very good model, right? So in that case, this error should be small. Another quantities, the last quantity here, it represents the approximation error. And in other words, it represents the capacity of the architecture we already choose. For example, initially we choose this family, right, in order to work with our problems. So the approximation error essentially says about the capacity of this family, okay? If this family is very short, it means that it can approximate very complex function, right? In other words, the best model in this family should be very close to the truth, right? Otherwise, we can say that our models or our family can be very bad. And it is represented in this kind of error, approximation error, okay? And we cannot avoid that. We'll choose a specific type of model, right? One architecture. Then it should have some approximation error. Okay? Any question? Okay, so let's see more about estimation error. This is where we can analyze and understand, and we can adjust, we can minimize in practice. Right? Okay, let's rewrite the training error to be like this. We add two more quantity. We just plus minus this quantity and add that quantity. So it is the same, right? And we do the same with this one. Okay, this is just a rewrite of the first one. Okay, but from this one, we can easily see that the estimation error can be decomposed into two other type of error. One is optimization, and the other is generalization. Okay, so what is that? Let's observe that um, these quantities show the difference between the empirical error and the expected error of our trade model, right? And of course, it is can be upper bounded by these quantities, right? Here we denote by a soup here. Do you know what is that? Soup. Do you know this notation? Yes, supreme. It is similar with maximum, right? More general than maximum. Okay, so the first two terms can be bounded by this quantity. Um, the last two terms can be um, represented by this formula, right? Because by definition, S0 star, it is a minimizer of the empirical loss, right? And in other words, we can write by this term. And the second one, because S star, it is the best model, right? So we can write that to be like this, right? And this quantity can be bounded by this one. Okay, that's very simple probably from maximum and minimums and something else, right? Uh, And therefore, we from the decomposition before, we can bound the error, the estimation error, to be at most the sum of these two terms. Whereas the first terms, you can see that this is the difference between the two models. One is the minimizer of the training error. One is our train model, actually, right? And these quantities represent the quality of the training process, the optimization process, right? In practice, we may use some optimization algorithm to train the model, right? So this quantity should represent that. Okay, so that's why we encode this to be optimization error. And the last term, sometimes we call that generalization error. Because here, it is measured the difference between expected error and empirical error, right? Okay, so when we want to understand the errors, you can focus on this type, right? Optimization error and generalization error. How about optimization error? It shows the strength or the quality of the training process, right? Of the optimization process, right? And in practice, our trained models can be very far from the minimizers, right? And this error can be high sometimes, right? How about generalization error? The difference between empirical error and the population error, right? Sometimes we call this, okay? And of course, we want this quantity to be small, right? You can see that when this quantity is small and the training error is small, then the test error should be small, right? So that's why in analysis, sometimes we can focus on this quantity, right? Okay. Any question? Okay, so it seems easy. Okay, so let's go. Um, so let's discuss what is the sources of error. We already decompose the errors of a model into different type of error, right? Optimization, generalization, and approximation, right? Now, we want to understand where is the sources of error. When we understand those, we can find some way to improve the training of the model, right? And we can hope that we can obtain better models. Okay, the first source can come from the data. And of course, right? We can easily see that. Sometimes your data can be very complex. The data space can be very complex. For example, here, just one example to represent the data space. In this case, it is simple, but when your data lie on this area or this space, it can be very complex, right? And of course, in practice, the data space can be very complex. It can be a manifold, or it can be a low-dimensional subspace. Even though our data is represented by a high-dimensional number of features, for example, right? But in fact, it can lie on a very low-dimensional space. It is hidden in in nature. So in those cases, the problem can be complex, right? And another thing is the data distribution, right? The way we collect the data. Sometimes the way we collect can be complex, right? For example, like this. We collect um, many points here, many points here, and many points here, but sometimes here are very few, for example. So in this case, the data distribution can be complex, right? And sometimes the training sample can be non-representative of the whole space. The whole space can be very large, and you just collect some example in a very small area, for example. So in that case, the training set is not representative, right? And of course, in that case, little information is in the training set. And we cannot hope that the training algorithm can understand about the data space. Okay, so that is the first sources. The second one is the model family you choose. Or in other words, the architecture you choose can pose some inherent error, right? And in practice, when you choose a big space, then the approximation error can be smaller. But when you choose a smaller space, approximation can be higher, right? Can you explain this? Why? Mhm. Oh, so in you were mentioning about the data size, right? The training set. Okay, so but the question is the model space, the hypothesis space. Yes. When you choose a big space or more complex architecture, for example, right? A more complex architecture means the model space can be larger, right? But when you choose a very simple architecture, then the model space can be small. For example, just compare linear model and a neural network with two layers, for example, right? So for the neural network, you can show that it is more complex than linear model, right? More complex, it means that the model space should be larger, bigger, right? Okay, so to see what, just see this example. When we choose a small family, model family, we can have this family, right? It is small. Then the approximation error can be here, right? The distance from Y star to the closest point. Right? It represents the approximation error. But when we use another bigger fabric that contains this one, okay, for example, this model, this family, then this family is bigger and contains this family, right? And of course, you can easily see that there exists some other models that can better approximate the unknown function, right? This is just one example. When we choose a more complex architecture, then the model space should be bigger, right? And in that case, the approximation error can be small. That's why many breakthroughs in AI research often use some very huge model. You know that? Trillion of parameters, right? So in theory, when we use that very huge model, the approximation error can be ignored, right? Can be very small, very, very small. So we can ignore that. Okay, but in sometimes we if we choose carefully, then we can only need one small family, but can result in small approximation. It is just one example. If we choose this family, right? So the approximation error should be much more smaller than this one, right? Although this family, HE, can be much more smaller, simpler, for example. But in practice, it is not easy to choose this kind of architecture, right? We can easily choose a very big architecture, and we hope that there exists more in that family to work with our problem, right? But when we use very simple models or simple architecture, it is very hard to choose which type of small architecture that can help us to work well with our problem, right? That's why in practice we often we often use very big architecture, very complex. In the case, if the model families contains one member with zero error, so in that case, sometimes we say that it is realizable case. There exists one member that exactly approximates, exactly fit the unknown function, right? And of course, in this case, our models should be very complex. Right? Any question? Okay. Another source can come from the training algorithm, right? From the learner. And of course, you can see this from practice, right? If we have a very good training algorithm, then it can produce smaller estimation error, right? But in the case you choose a very bad learner, then it can produce a very bad model, right? And in that case, um, the estimation error can be high, even though the training error sometimes can be small, but the test error is still very high. And in that case, the trained model can be overfitted, right? So in that case, the learner can be very bad. Okay. And a good learners should localize a subset of the model space so that in that areas there exist many good models, and then it can return a good model, right? That is a good learning algorithm. Okay. And in practice, we may have many different kind of learners. For example, you already know about Lazo, right? It is very well known algorithm, and it can help us train a linear models, and of course, it can help us to train more complex models, right? And the idea is to use L1 regularization. That's all. So that's why it can often produce some sparse solution. Okay, so this is one kind of bias of a learner, right? We just focus on some sparse solution. So this means that in practice, each learners can have some bias, right? Some specific preference. it can produce some trained model with some special property, right? This is just one example. But sometimes you can use other learners that can produce a model with low complexity. For example, um, in your model, most ways is small, right? This is one kind of bias for the learner, the learner, right? But sometimes a learner can produce can prefer some more with which are robust to the input. And in this case, the trade model can be variable robust, right? If we change, if we make a small change in the input, then the output essentially the same. So that model is robust, right? And it can help us to 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 face with some attack. But sometimes your algorithm can produce some model that is very robust to the noise added to the weight, for example, right? And sometimes your learning algorithm can be stable. Right? If we have some change to the training set, right, then the trade model essentially is the same. Okay, so in practice, there are many learners, many learning algorithms, right? And each one should have different property and preference, right? You need to know that in order to analyze what is inside when we get a very bad model, right? And of course, those biases and properties should affect the generalization probability of a learning algorithm, right? Okay. You have any question? Hey, one question. When we work with VAE, is this a learning algorithm or a model? Which one? VAE. Okay. It is a model or a learner. um, Quang Ha, what is your opinion?
Sorry, can you repeat the question?
Okay, so the question is, consider VAE we studied before. So, according to your opinions, it is a learning algorithm or a model. Do you see the question? Quang Hà, do you have answer?
Sorry,
Hey, how about Kim Tuyến? Do you have any idea?
I don't have any idea. Teacher, can you listen to me? Teacher, can you listen to me?
Okay. Anyone? Do you have?
Sorry, but I don't have any idea for this question.
How can I answer it?
Yes.
VAE actually, for me, this is model.
Mm-hmm.
Yes,
This is tomorrow.
yes, me like that because it actually what is the model? Model is basically it is a assumption or the function that we will be find the function that will be mapped from X to Y. Basically, it is like that, and the learner the actually is a way that to have the model can be learn the parameters about weight or bias. Actually, the learners something like Australian descent or stochastic or anything like that. It's just a way that we can find the parameters.
Mm.
So so by the definition of that of the model and learner, so I think VA should be it's with models, right? It actually it's like the generative model, right? So it could be help us to find but for me like that. VA is model.
Okay, very good. How about the other ones? Do you agree with him? Okay, so last thing about that. And in practice, for one model, we may have different algorithms for to train, right? So each algorithm can be considered to be a learning. Okay, and a learner should be different from a model or the model space, right? And sometimes we can analyze the error of a learner because it produces some train models, right? And we want to analyze Okay, so let's take just one example. Let's consider the regression function, y star x. And after training, the learners can produce one regression we denote by AD based on the training set D, for example, right? And we hope that the trained model should approximate the truth very well. Okay. However, in practice, the training set can have many uncertainties, right? A lot of uncertainties. For example, different people can produce different training sets. And sometimes the training set can have some noises or some errors, right? So this function can be random. When we change the training set, then the trained model, the output should be different, right? So in order to analyze the errors of a learner, we need to consider these to be random according to the training set. And then we can analyze the error of one prediction, right? For example, for these models, the error can be measured by the square error like this, right? This is the truth, and this is the prediction, okay? But this is the prediction for this is the error of one specific model, right? But for one algorithm, it can produce many different kind of models according to the different training set, right? So in order to see the error of one algorithm, we need to consider this quantity. It is the expected over the training set of the square error. Okay. So here is the errors made by the algorithm, by the loader. We need to take the expectation over the whole training set, right? We consider different training set. And then what is the train model? And then we measure the error from those predictions, right? Okay, so and this quantity can help us to analyze one algorithm, right? The error from algorithm. And of course, sometimes we can base on this to analyze generalization ability of a learning, right? Okay, so in summary, we can have this graph to show the error. The error of one prediction can be caused by different factors, right? For example, it can be the optimization error and generalization error and approximation error, right? It had many different type of error, and each type of error can be caused by different factors. For example, approximation error can be caused by our specific architecture, right? When we choose one architecture, it can produce some approximation error. And of course, it also depends on the data space, the data distribution, right? Okay, how about optimization? It depends on the learner, right? And of course, and depends on the data, right? Data space and data distribution, right? And of course, the model we choose, right? When we choose very small model, then the optimization error can be small. If we choose simple model, then the optimization error can be small, right? But when we choose very complex model, very complex architecture, then optimization error can be high for bad learning, right? You see that? And another error is generalization, right? And this error can come from different factors, right? So all of these can cause some error to the overall error of one fraction. So if we want to analyze the errors of a model or of a learners, for example, you need to consider some of these factors, right? Okay, any question? Okay, so in learning theories, there are many theories that are trying to analyze the error from different view. For example, if you want to analyze the approximation error, then you need to consider the capacity of each architecture, right? Each small family, and essentially, we need to estimate this quantity, right? The error of the best model in the given architecture, okay? But in the case, if we want to analyze the optimization error, essentially, you are trying to analyze this different, right? We need to understand the probability, the key probability from the optimizer you are using. And you need to bound to estimate the error, right? For example, we can provide some upper bounds on this different, for example. If this upper bound is small, means that your learner can be very good. The optimizer can be very good, right? In the case, if we want to understand the generalization ability, for example, after training, how well it can perform on test data, on unseen data, for example. So in that case, you need to analyze this kind of error, right? That is a difference between the training error and the test error, right? Or sometimes we just focus directly on the test error, the population error. Just focus on this, right? And this is the ultimate goal. We need to train a model that so that the population error should be small, right? And in that case, this model can work very well with unseen data. And in theories, we often focus on an upper bound for this difference, right? Because the exact difference here cannot be computed directly, right? So in order to analyze this probability, one way is to analyze upper bound on this quantity, right? And one direction is we can consider the worst member in the architecture, okay, in the family. So in that case, essentially, we try to estimate the supremum of this difference. If this supremum is small, means that every members in our family should be good, right? Should generalize well. So that's why this quantity is many years ago, many theories focus on this quantity, right? We are trying to see the worst member in the model family, okay? In other words, we are trying to provide some upper bounds from that quantity, right? But one thing is, when we focus on this one, focus on the worst member, sometimes it can be very bad, right? So in that case, this quantity may not reflect the quality of our trained model, right? It might be very different from our trained model. So this kind of analysis sometimes is very sometimes it is useless. But sometimes it can be useful. In the case you want to analyze the whole family, right? Each architecture, right? We use a linear model, or we use a neural network with 2 layers, for example. Once we choose that architecture, and we want to analyze what is the worst member in that family, for example. So this type of theory can be useful. Okay. Another way recently has been studied very actively is PAC-based BAO. Instead of studying the worst member, we study the average error over the whole space. The space here is over all the model in the family. That is, we want to study about this expectation. Right? The quality of one model on average, what is that? And we want to estimate that, right? So you can see that this quantity should be closer to the error of the trained model, right? Compared with the worst memory. So that's why there are many recent research trying to focus on this quantity. And a good news is some recent research can provide very accurate error estimate for some big model, okay? Even for some GPT model. That is very good news. Otherwise, when we focus on this type of analysis, this quantity often very huge and vacuous or meaningless. Okay, any question? Okay, so let's focus on generalization ability of a model. It is very practical relevance, right? In practice, we can train the models, and we hope that the trained models can work well with future data, right? Unseen data. And essentially, that model should generalize well. Okay. Let S0 should denote the trained models. And it is trained from a training set D, right? And it means that it is a function of the training set. It depends on the training set, right? And in other words, it is a function of the training set. So sometimes we can write something like this to show that this function depends on a data set D, right? Sometimes it is useful for analysis, right? Okay. And we want to analyze this function is a generalization everywhere, right? Or in other words, we want to estimate the population error of that model. Right? And when this quantity is small, means that the model can generalize well. Right? Otherwise, the model can be very bad. Sometimes overfitting or sometimes underfitting, right? But here, we cannot compute this quantity directly because P is unknown, right? The data distribution is unknown. So we cannot compute this. But when we have a data set D, we can compute the error on this data set, right? And of course, when the data set, the training set is changed, this quantity is also changed, right? So in theory, if we want to analyze this, we need to consider this fact, because there's some uncertainty in the training set. Sometimes noise, sometimes error, sometimes randomness, according to different sampling, right? So we need to account for those uncertainties in order to make a reliable estimate about the error. Sometimes you can obtain a very good training set, but sometimes you can have very bad training set, right? For example, your training set is very small, or sometimes it is very noisy, or sometimes biased, or non-representative, right? And in those cases, the training set can be very bad. And it can lead to very bad model, right? Okay. So how to estimate the error? Here we want to estimate the expected error, not the error on a training set, right? If we have a data set, then we will compute the average error on that data set. But here the true quantity is this one, the population error, right? So in theory, we need to estimate that. And as we discussed before, there's some uncertainty in a training set, right? And it means that there's some uncertainty in the model, in the training model. We need to account that in order to have some reliable analysis, reliable estimate about the error, right? So essentially, we can borrow some idea from probability. That is, we want to make some statement like this. We want to show that the probability that the population error is larger than epsilon should be less than delta. Okay? Or in other words, we want to state that the population error is large with a very small probability. And in that case, our model can be very good, right? With a high probability. That's our way. And by this way, we can account for some uncertainty in the training data, for example. And here, epsilons can be considered to be our estimate about the population error, right? Epsilon here, it is about an upper bound on the population error or the test error, right? That is our estimate. And of course, delta represent the probability that our estimate is wrong. Or in other words, it represents the probability that we get a very bad training set, right? And in practice, we hope that both epsilon and delta should be small, right? Epsilon small? What do you mean? The test error should be small with a high probability, right? If we have this kind of statement, then in that case, our model can be very good with a high probability. So that's why in practice, we often try to find this quantity. And we hope that those quantities should be small. Otherwise, our model can be bad, right? So by this way, we can write by another way. This fact, it is we can write in another way, right? The probability that the test error is at most epsilon. It is equal to this one, right? Here we are representing the probability according to the sampling of the data set, right? Of the training set, okay? So this is another way to represent that, okay? And in order to say that S0 is good or the test error is small, then this probability should be at least 1 minus lambda, right? Okay, so this is how we need to show when we want to have a reliable assessment about a trained model. And sometimes these quantities, we say that it is a confidence, right? We have one prediction about the test error, and this one represent our confidence about the estimation, right? Once we show this, it shows that our trained model can be good, right? With a high probability. Okay. Any question? Everything okay? Okay. Once we show that, we can say that S0, it is approximately correct predictor. And by that results, when we do not have that results, and in practice, sometimes the expected error of this model is greater than epsilon. And in this case, the test error can be high, right? And this shows the failure of the learning, right? Otherwise, this model can be considered as approximately correct predictor with a very good accuracy, right? With a very good error. And it can generalize well, right? Okay. So in theory, if we want to estimate the error, we want to estimate epsilon, right? Okay, and one way is we can upper bound the probability of this event, right? The event that the population error is greater than epsilon. What is that probability? Okay. And in the case, our training set contains some IID sample. That is, the sample are independent, right? Then we can consider the training set to be generated from a distribution we denote by P power M. To be like this. It is a product of m different distribution. Okay, this is another way to write. So we want to estimate this probability. It is similar with this one, right? The probability that we can have some the set of every bad training set, right? It is set of D so that the test error is greater than epsilon, right? If we know this, we can estimate, we can have a good estimate about the test error, right? With a high probability. But sometimes in practice, we want to do in another way. For example, we can want to see a low bound on that probability. That is, sometimes we want to consider the worst case or the hardness of a learning problem, for example, right? Sometimes. So in that case, we need to consider another way. Not upper bound, but lower bound, right? For example. Okay, so let's return to a very basic concept in machine learning. It is learnability. The keyword is very natural, right? Learnability. What is learnability? How to formalize that? We are working with machine learning. That is, we are trying to make some machine that have some ability to learn, right? But what is that? How to define that? And a long time ago, this is a big question. And until 1984, there's well-known researchers. It is Leslie Varian. He is very great in computer science, and he developed a theory. And now we say that it is a PAC model. And from this model, he was awarded the Turing Award in 2010, about more than 15 years ago, right? They know that this award, it is considered to be a Nobel Prize in this area, in computer science. Right? So in these models, he formalized what is learnability and how to define it very clearly. Okay, this is how. Let's consider a hypothesis class H. We say that H is PAC learnable if there exists a learning algorithm and a function we denote by MH that map from this Q to N with the following property. For every epsilon and delta in this area, and for every data distribution P over X, and for every labeling function, if the reliable assumption hold, then when we run the learning algorithm on MIID sample from distribution P and labeled by Wi-Fi, then the algorithm will return a hypothesis S0 such that the test error is small with probably at least one minus standard over the random choice of the training set. Okay. Or in other words, it satisfies this equation. Okay. And in this case, we can say that the model class H is PAC learnable. Well, here we use one assumption. It is reliable assumption. Here is what's that? We assume that the model family is strong enough to exactly approximate the unknown function. Okay, that is the best model should have zero error, and in that case, we work with reliable case, right? And in this case, this model family should be very complex, right? Very strong. And and if it satisfies this condition, then it is learnable. Okay? Or in other words, it can approximate the unknown function, right? It can approximate exactly. And many of its members can approximate very well. So in that case, this family can be considered to be PAC learnable. Okay. So when we use these models, we need to define two parameters, F1 and delta, right? S1 here represent our prediction about the test error, right? And delta represent how likely the return model can meet the requirements about the quality, right? Or in other words, one minus delta here show our confidence, right? The confidence that our estimation about the test error is. And of course, in practice, in practice, this assumption, reliable assumption, can be very strong, right? And in practice, we can choose some simple model, a simple architecture, and in that case, this assumption can be wrong, right? So that's why we should relax the definition about learnability before to work with this case, more general case. Okay. In the case, the best model can have some wrong prediction, right? So in that case, the learning problem can be hard, right? And in that case, the model family can be small or not strong enough to approximate the routers, right? Okay, so in that case, you can modify the definition before in order to work with this case. For example, like this. Okay, if we are sure that the test error is not very far from the best models in the family, in the model family. So in that case, we can say that this family is learnable, PAC learnable. That's all. Okay, any question? Okay, we may have some minutes break. Okay. Okay, so let's continue. So we already know about a learning algorithm, right? And we say that this algorithm and this problem is learnable or not, right? And when we work with a model or one model families, right? And we can consider that to approximate or to learn the unknown function or to solve the learning problem, right? And we have one way to analyze that, to answer that. If we show that our models, our model families can satisfy this constraint, that is, there exists a learning algorithm that can return a hypothesis or return a trained model satisfying this constraint or this requirements, then the learning problem is learnable, right? And it is learnable by our model family, right? Okay, when we have this definition, we base on one function, m8, and this function depends on epsilon and delta, right? And here, this function, sometimes we call that it is representing the sample, the number of samples, in order to assure a good model, right? And the minimum number of samples required for learnability. In that case, we call that to be the sample complexity. And of course, each family should have different sample complexity, right? Okay. In the case, if we focus on if we work with a very complex model family, and in that case, the reliable assumption can hold, right? That is, there exists a member in that family that can accurately approximate the true function. And in that case, the sample complexity of this family is bounded by this quantity, right? Here we denote this numbers. It represents the size of the model family. And of course, when we write this, we are assuming that the model class should be finite, right? So if the model family satisfies a reliable assumption, then we can estimate the sample complexity, and this is the upper bound for the sample complexity, right? And it means that it is very good, right? Sometimes this hypothesis family can be very good. It requires a few number of samples in order to assure that the trained model can be good, right? Can be accurate. And in practice, especially in the definition of learnability, we often require M to be a polynomial in the two parameters, epsilon and log delta, okay? Do you know why? Otherwise, this number should be exponential, right? Exponential in this quantity. And what it means about exponential in this quantity, we can we can see from the bar before, in this case, we will require an exponential number of samples in order to assure that we can train a good model. And in that case, your model family can face with the curse of dimensionality. And it is very hard to train a good model, right? So that's why in the definition, we often require the number of samples to be polynomial in this quantity, right? And when we work with some learners, sometimes we can observe some very common behaviors. Some algorithm is very strong. We can apply that for many different kind of models. For example, we can use some algorithm in optimization, SVD, for example, right? It is very strong optimizers, and in the area of deep learning, you can have it to train a good model very easily, okay? And it means that this kind of learner is very strong, very good. And when we provide more training sample, or when the training size is increased, then the performance of the trained model can increase as well. That is a very common properties. And of course, we consider the case the training is good, not very bad, right? So this is a very common property. But one question is there any learners that can learn any function just by increasing the number of samples? Because we have this property in practice, right? So a natural question is, can we learn any problem? Can we solve any learning problem just by increasing the number of training sample? And the answer is no, not easily like this. We have a very well-known theorem. It is no freelance theorem. It essentially says that for any learners, there exists a learning task so that the learners can produce some trained models that are very bad, even though there exists a perfect model for that problem. So in other words, this essentially says that one algorithm can be best in these areas, but it may not the best for some other area, right? Some other problems, some other domain, for example. So essentially, in practice, you need to choose a learner carefully when we work with different problems, right? In different areas. Otherwise, you can face with some very bad trained model, right? This is the essential of no free lunch time. And here is the exact formulation, okay? You have any question? Okay, so in the next part, we will study about analyzing generalization in more details. We will take some example how to how to analyze and how to use some results in statistics to help us to to analyze generalization problems. Okay, and then some popular approach recently. Researchers are trying to analyze generalization of the trade models. Okay, let's remind about the trade models. In practice, when we train the models, when we use a learner to train, it can produce a model that depends on the training set, right? And these quantities can be considered to be randoms because it depends on randomness of the training set. And sometimes randomness from the learner, right? Sometimes the learners can produce some randomness. Do you see that? Some learners or some learning algorithm, some training algorithm can produce some random noise. Do you see it somewhere? No, not yet. Have you trained any model before? No, never. Oh, you should train some model. Otherwise, you do not have empirical experience, right? And in this lecture, we just focus on theory, okay? But in practice, you need to do many experiments to get some insight from practice. For example, the noise or randomness can appear when we train a model. Do you see that? Do you have some example? Hmm. Okay, that is one example. That's why it is named stochastic, right? Is there some stochastic things inside the learner, inside the training process? Okay, so it means that the train model can contain some randomness, right? And the cost can come from different sources. Okay, but when we want to analyze generalization, we need to assure that those randomness should be accounted should be considered, right? Okay, and we need to assure this statement in terms of probability, right? We need to say to assure that the test error of the train model should not be far from the best model, right? Okay, but another way to analyze generalization is to consider the difference between these two quantities. One is the training error, and the other is the test error, right? The population error. Okay. Or another way is we just focus on the population error directly, right? Okay. And by the law of large number, when the training sample is independent, right? So you know that the training error when goes to the test error, the population error, right? When the size of D increase to infinity, right? And we hold this with probability 1. This is a law of large number, okay? And it means that we just use the training error. Training error can be very good to estimate the test error, right? But it is only true in the case the training side is very huge, right? And in practice, we may not have. And the training side can be small sometimes, right? So we do not have this. And these two quantities can be very different, right? Okay. And another thing is, by this law, we do not know the conversion rate, the rate that this quantity will go to this one, right? What is the rate? We know that it will go there, but how fast? How fast it is, for example, right? We do not have exactly. Okay, in statistics, there's a very well-known theorem. It says about the relation between those two quantities, the error on a finite set and the error on the population, for example. Okay, it is what. Let's consider Z1, Z2, and Zn to be IID. And the function G, which is independent from those Z, then for every epsilon, which is positive, then we have this difference is greater than epsilon, with probability at most to be like this. Here we denote exp to be e power. We denote like ex e a is impact e power. Okay. So this is a very classical in statistics, and it says something about the difference between the two, right? One is the average on a finite set, and the other is the expectation, right? And it is very close to what we are considering here, right? Okay, well, let's discuss more. When we denote the right hand side here to be delta, right? Then from this quantity, we can write something. Then um, 2m squared over e a, right? From this, we can take the load of both lines, and we will have both delta. That is one. This will be, and from this we can write something about atoms.
Sorry. Sorry, your microphone is off.
Oh, so sorry. How about online people? Have you here? Can you hear?
Yeah, yes.
Yeah, yeah.
Okay, so sorry, some minutes before, we had some internet connection issue. So in this case, we have very good upper bound for the different, right? But we cannot use this for a train model because for this result to obtain, the g function must be fixed. That is, the g function cannot change when we change z. And when we apply this to a train model, the z function can be changed when we train a model, right? So we cannot use this result directly to analyze our training model, okay? Because the training model depends on the training set, right? Okay, but this inequality is very essential. Sometimes it can help us to provide some idea to analyze some training model. Okay, when we have this, it means that there exists a sample or there exists a data set D of size S so that this inequality is satisfied. And the set of those data set, the set of all of those data set can be large, right? Because we have the probability of D is at least 1 minus delta, right? But in practice, we may have a different data set for training. And then this statement may not apply, right? And when we have a training set, when we have a specific training set, only some members in the model family can satisfy this result. And those members may be different from the trained models we obtain, right? So that's why we cannot apply the Holding results directly on our trained model. Okay. So in that case, we may need to find another way to analyze the generalization error. Okay. And one very classical way is to use uniform bound. That is, we analyze the worst case, right? The worst case. If we train a model, what is the worst case? The worst model in a family, right? Here's how we analyze the worst case. We analyze the model that produces the largest generalization gap, right? If we show that this gap is small, means that our trained model also have small generalization gap, right? That is one idea and classical idea. And of course, the remaining task is to to bound these quantities, right? And we hope that this quantity should be small. Okay, so let's consider the case our model family only have a finite number of samples, not finite number of members. Okay, not infinite. Let's consider the case, the finite case. Okay, and assume that the number of members in the model family is n. Okay, so let's enumerate the number of data set, the number of back data set. So for each members, HI in the family, we denote GI to be the back sample so that this difference of error can be large, right? Okay, so from holding inequality, from holding result, we can show that the probability of DI is equal this one, right? The probability of DI so that this difference on error should be large. And by holding, because DI is independent with HI, so we can apply holding result. Okay, so this probably is at most this quantity, right? Okay, and then for two different data set, DI and DJ, the union bound provides this quantity, right? That is the probability that the union of DI and DJ is less than the sum of the probability of those two subsets. And then if we apply for every other data set, every other back data set, so we will have this one. Okay. And from this, we can obtain, we can use this one with this one, right? And we unify all of this result into one. So essentially, we can say that there exists the probability that there exists a member in S, so that the generalization error is large. That probably is at most this sum, and then at most and multiply by this quantity. Okay. So in this case, when we have a finite number of members, then we can estimate this quantity very easily. Okay. And by that way, we can say it another way. With probably at least one millisecond, every member in our family should satisfy this result. So we just take just one example to show that we can analyze generalization error of a model, right? By considering the worst case behaviors of any members in the family. Okay? And by this way, we can see that as m goes to infinity, this quantity should goes to 0, right? So the error of the empirical error will go to the expected error. So this result is good, right? In the case, if we have a large data set, then this quantity should be small. Okay. So it means that this model class is PAC learnable, right? Any question?
No.
Okay, so by the argument before, we can use that for one learning algorithm. It is EIM before, right? For the EIM algorithm, we just minimize the training error. So in the case of reliable assumption, it means that the best members, the best members in the family should have zero error, right? So in that case, the empirical error is also zero. So applying the results before, we obtain this result. Okay? We can estimate the test error for any members or any models by the EIM algorithm. And the test error is upper bounded by this quantity. Okay? Very simple, right? And of course, you can see that when the number of training size increases, this should go to zero. And it means that the ERM algorithm can be very excellent, right? It can produce a model with zero error. So it means that this model family is a PAC learnable by definition, right? And the sample size for these members can be calculated by this one. Okay, that is very good. Okay. And of course, we study those bounds, those results in the case that the size of the model class is finite, right? It is finite. Here is the size of the model class, the number of members in the model class, right? It is finite. Then this number can be finite, right? And it can go to zero. But in practice, when we choose one model family, it can contain an infinite number of members, right? For example, if we choose a linear model, it already contains an infinite number of members. So in that case, we cannot apply the result before, right? Because here should be infinite. So this bound should be useless. Right? And how to work with this? Because most models in practice, the number of members can be infinite. For example, the weights are real numbers, right? And it means that the model family should contain infinite number of members. Okay. But it leaves the problem to be very complex if we want to analyze generalization. Okay. And up to now, there are many different approaches. For example, we focus on the learning algorithm, but sometimes we can focus on the model family, the probability, the special probability of the model family, and then we base on that to analyze the generalization error. And sometimes we can focus on some specific probability from the data distribution or the true labeling function, for example. If we know some probability, we use that to help us to analyze the error. Okay. And when we focus on the model families, that approach is often called complexity-based bound. We base on the complexity of the model family, right, or the capacity, right. But when we focus on the learning algorithm, we may work with algorithmic approach. Okay. Otherwise, if we focus on the data distribution, in that case, we may follow the data-dependent approach to analyze generalization. Okay. But sometimes in practice, you want to analyze the error of your specific train model, not the whole family, right? After training, you want to estimate its error to know its generalization ability, right? So in that case, you just focus on one specific model. And if you want to do that, you are working with model-dependent bound, model-dependent analysis, right? Just focus on one specific model. Okay, so up to now, there are many different approaches. How are your opinions? Which one can be easy compared to some other approach? Which one? The last one? Or which one? Okay. um, it is unclear which one should be easier. And of course, some of the most classical way is to analyze a family of model, the model family. And it means that we are trying to analyze the complexity of the model we use. That is one of the classics, the oldest way to work with. And then another way, recently, we can analyze some theory of the learning algorithm. Okay, and based on that, we can estimate the error, the test error. The other way seems to be more complex because the data distribution we do not know, right? The learner we know. If we choose a specific one, right? SCD, for example, we know some probability of SCD, and then we use that to analyze. But for this approach, we just have some training sample, right? Do not know the true data distribution. So this approach should be very, very hard. And of course, it is also hard for the trained model. You know why? The last one. Maybe hard disk. Yes, can I explain one? Mhm. Mhm. Okay. Another reason you said about the matrix, right? Um, different application may require different matrix. Okay, and there's some conflict about matrix. How about the other opinions? A train model. After training, we already know that model. Okay, but why? Why analyze that? Analyze the test error of that model can be hard disk. So that's why most theory in machine learning do not focus on this. Does not approach this one. Mhm. Mhm. Mhm.
You can only make only have very small space for making assumption and for like previous experience. That mainly the theoretical results. Uh, if in a way it could really optimize the assumption can be strong, for the case of regulatory model with another space with some such strong assumption.
Mhm.
Space to, for example, like a class model, you only get one model.
Mhm. Mhm. Yes, we have only one specific member in the family, right? And we do not know the data distribution. We just have some sample from the training set or some other sample from the validation or test set, for example. Okay. And we may not know what exactly appeared in the training process. So that's why most prior theories focus on these two approaches. Okay, it is easy to analyze. For example, one approach is focus on robustness. They are trying to analyze the robustness of a learning algorithm. Okay, and the idea is there's some connection between the robustness of a learner with generalization of a trained model. That's very good connection, very great connection. Okay. And this connection has been discovered about more than 10 years ago. And, and here is the results. For example, um, let's ask one D to represent the robustness of a learning algorithm. Then we can connect that to the generalization error of a model, of a trained model by this result. That is, the test error is bounded by the training error, and robustness of the learner algorithm, and this quantity, this uncertainty. Okay, that is very clear. So it means that if our learners is robust, this quantity should be smaller, and means that the trained model can generalize better. It essentially say something like this. But well, what is robust here? Here is how we define. Essentially, two different two the laws of the two close points to be small. That's all. Essentially, it refers to something like this. Two close points should have similar laws. Okay, and it is upper bounded by epsilon d. Okay, And this quantity represents the robustness of the learner. A small change in the input should produce a small change in the loss. Okay, and in that case, it is called robust learning. And of course, the trained model should also be robust, right? A non-robust model can be sensitive to some attack in practice. So a robust learner can produce some robust model, right? And a robust model should have this quantity to be small. And it means that generalization error can be small as well, right? That's a very good connection. And of course, the reverse is not true. A model with very good performance sometimes can be non-robust, can be sensitive to some change in the input. Have you heard about something like this? A trained model can be sensitive to the input, to a change in the input. Can be very easily attacked by someone. Have you heard about this before? Okay. So by this approach, there's one trade-off between between the robustness and the way we divide the data space into a large number of areas. Okay, and from this theory, it can provide some idea to train a good model. For example, we we should assure that the learner should be robust, right? And a trained model should be robust. And then by this theory, the model can generalize well, right? And also robust and can face well with adversarial attack. And in practice, many algorithms can be robust under some conditions. Here's just some example. For example, Lozo, PCA, mixed machine learner, for example, SVM, right? And neural network can be robust. And of course, the robust number here can be large, right? Can be large, but can be considered to be robust. Okay. But for those theory, we need to divide the data space into a large number of dimensions, a large number of areas. So sometimes it can be vacuous, or it means that this this upper bound sometimes can be very large and trivial sometimes. Okay, and in that case, this bound can be useless. This is just one example. In the case, the model only had one incorrect prediction. So this bound will be useless because this number should be very large in that case. Okay, and in practice, we may find some way to analyze some other property of the learners, and then we can make this bound to be more tightened, for example, and then we can help her to train the model better. And recently, I have some analysis about this approach, and and find something serious with this theory. Okay. Any question? Yeah. Mm-hmm.
I think about the I think there are there are a few line research that dynamics of model. For example, like how fast the model converge, how well it generalize. There is something that they make the theoretical analysis on a relatively simple class of models. And usually it is one or two layer model. And they and geometrical results that their estimation or their approximation is fine. And I think that the algorithm is relatively successful to the class of free transformer networks, for example, like in the case of CNN or the DNA. However, when it comes to transformer, I think they are less pronounced research. They are feeling that they are probably aligned with their results are not that good. For example, there are results about the NPK or similar results. And I want to ask why the theory of learning dynamics on the generalization gap is not as effective as it was before. I mean, like, why does the theory works well on the CNN or DNA-based classic models and not the transformers one? I'm suspecting that it is because it is due to the nature between the two classic models. One we just convert the result, although one significant different the transformer is that they have the products of two or three entities that are undergoing the free trading. So maybe that's why they kind of aggressively are the language. But I just don't be sure about my assumption, so I ask you more on the topic.
Oh, you know a lot. I'm surprised. You said about something very, very deep and recently about learning theory and deep learning theory. Okay, and you mentioned about MTK, and those results is very interesting, and they can help us to analyze some simple model. For example, a neural network with 2-layer, 3-layer, but one fixed layer, for example. Okay, and in order to analyze some complex model like this, they need to use some explicit probably from the learning algorithm or from something else, from the model architecture, for example, right? For example, when we focus on SGD, it in every iteration, we compute the gradient and use the gradient to update the model, right? And from simple model, we can compute the gradient explicitly, and then we can use that simplicity to analyze the dynamic of the weight over time. Okay, so but for complex model, the gradient should be very complex. So that's why beyond 3 layers, those approach should be failed. The gradient should be very complex, and it is very hard to analyze the gradient, the dynamic of the gradient. Okay, that might be one of serious reason, the major reason.
So in a way, it's relatively correlated to the phase of the model, which had already trained in one analytic generalization capability. Because in such phase, we might want minute architecture have the best capability when it comes to implementation. And I think actually that many zero possibilities if we definitively out on CNN-based model. However, the results kind of change when they come to the transformer-based space. So that's why I kind of raised it. I think that the problem lies within the nature of computer.
Yes.
So maybe can I explain the
Yes, the architecture itself impose a lot of difficulties for some approach. For example, if we try to analyze the complexity of the model, for example, by that way, if we go to a more complex model, it should be more complex, right? It's not easy, and sometimes if we use the complexity of the family, sometimes we can arrive at a very bad upper bound, or sometimes trivial, for example.
Now, I mean, both the CN versus space and the transformer versus space are complex.
Mhm.
And the metrics based on the dynamics does not really show high correlation through capability of each model.
Mhm.
And I think that it is because of the different, like I said, the growth, the products of several underlying entities. So it can have a different kind of physics compared to the that's not really possible.
Okay, so estimate the test error of a trained model is still a challenging problem and open in deep learning and in learning theory. And recently, I focused on these problems, maybe more than 2 years. And recently, I obtained some very good results. And I want to share with you just few information. Okay. And the way the ideas in my approach is we can analyze the errors of models in different areas in the data space and then make a summary in order to have the overall errors for the model. As we can see from these figures, the error from different areas in the data space can be very different, right? In some areas, the error can be very high, but in some areas, the error can be very small. And the distribution is very non-uniform, right? And the idea in our approach is how to use those information in order to analyze the test error. Or in other words, the idea is to use something like the geometry of the data distribution. Geometry. Even though we do not know the data distribution, but based on some sample, we can estimate the geometry, the complexity of the data in this different area. And then we estimate the error in those local areas. And then by some way, we can aggregate those areas in a peaceful way. Okay. And here is how we can aggregate. We can compute the error. For example, the test error can be bounded by the training error and plus to some other quantities. One quantity is relating to the geometry of the models of the data distribution. It is represented by this quantity, and another quantity relating to the alignment between the model and the data geometry. If the model align well with the data geometry, then that model can generalize well. That's very interesting. Okay, here's how it can show. If there's a good alignment about the loss of the model and the data geometry, then we can show that the test error should be good. Okay, and the model can perform well. Okay, and that is the general theory. And in practice, when we compute on some model like this, sometimes the model is very big, and of course transformer can be here, VIT, for example. Okay, and here's the result. The test error is like this. Okay, for example, this is a test error computed on a very large data set. We can estimate the test error. Okay, here this is what our theory can estimate. And up to now, this is the first result that can estimate a good test error like this, even for a very large model here. So that prior theories do not know or do not have this ability. Okay. Okay, so there is just some information that in our recent research we obtained something like this, and maybe in the near future there's some answer to the main question, the open challenge in this area. Okay, any other question? And of course, from this theory, it can suggest you some way to train a model better. The model should align with the data distribution, align with the geometry.
Should be data. And I think some way to do that we are not just exploring the capability of the geometry, but we are
Mhm.
exploring the behavior of the itself.
Yes.
Asking basic model means that we're given a specific behavior of the finding areas as like the model behavior to stay actually putting out correlation on the gradients, or maybe some kind of order of these machines. And definitely happy with the
Here is just some guide to train the model. There's some quantity where I call that align to show that the error in different areas should align with the density of the data. Okay. If you assure that that quantity is small, then the model can perform well. Okay. Okay, maybe I hope that this work will be available online, freely online in near future. And in that case, you can see what is here, and you can use it in your training process, complex model, for example. Okay, any more question about this lecture or the course? Because today is the last lecture, right? For the next week, we will hear some presentation from different group. Another thing is, I have a talk in this Sunday. If you have time and want to understand more about deep learning, you can join. Okay, this is where this is what I will talk about the work I just mentioned before. And it will be VIASM. Yes, here is where the workshop will take place. Yeah. No. Yes, you can ask some other group to yes to change.
Presentation is
18, 18, right? So it is after your trip, right? Before? Mhm. Oh, because I heard last time you said that you will be back before 60, right? Hmm. After 12. Okay, so in that case, can you ask some other group to have some change? Yes. Yeah, so just try to make a change with another group. Yes.